So let me introduce our speakers. I'm really excited about this. We're going to hear about research from two students from SUNY New Paltz. So this is a team. Stoker is an astronomy major here at SUNY New Paltz. They were born in Pasadena, California, and began college at Pasadena City College, but then transferred to New Paltz. And Stoker took the planetarium operations course with Raj here at New Paltz, and they are now a current planetarium presenter. Stoker also works at Barnes & Noble, where they have set up a wonderful display of books about the eclipse. So if you go to Poughkeepsie and go to Barnes & Noble, yay Stoker.
Like a sun and moon decoration. You can move
right, you can move it. You can move it so gently. You can make your own. Is it on a pull chain, or you just have to?
It's just on like a ribbon.
We should talk about motors. Maybe we can put a little motor.
I have a budget for.
Yeah. Okay. Well, I have a budget too, and maybe we can collaborate. So, okay. So Stoker is going to graduate this spring from SUNY New Paltz. Dylan Sczerba is an astronomy major also here at SUNY New Paltz. He's also doing a minor in geology. He grew up in Poughkeepsie and in Newburgh, and he's currently from Fishkill. He also took the planetarium operations course here at SUNY New Paltz. That's a special thing here. And he's also a current presenter for our astronomy, our planetarium shows. He is currently the vice president of the Cosmic Club here at SUNY New Paltz, and he will graduate also this spring. So Stoker and Dylan.
All right. Hello, everybody. I'm Stoker, as Dr. Myers introduced.
And I'm Dylan.
We did some research on Supernova 2023 IXF that we're super excited to share with you guys. All of this research was conducted here at SUNY New Paltz in the Smolen Observatory. And our advisor is the lovely Dr. Amy Bartholomew, otherwise known as Dr. B. So let's get started. So why are we here? So we studied a supernova that went off back in May of 2023 at the observatory here on campus. We spent 6 months imaging this supernova to collect all of our data, during which we encountered a lot of issues, a lot of problems, but we managed to refine our process and we managed to overcome the obstacles we faced to eventually end up with a result of 100+ images of the supernova that we can use to quantify the supernova's brightness. And then we made graphs which show how the supernova changes over time, which we call light curves. And we kind of looked into what physical processes contributed to certain parts of the light curve. And since this was our first time doing research, we think it really helped make us better astronomers, better people even, maybe. And we're really excited to share it, to maybe even help other people as well.
Introduction. So when was this supernova discovered? We unfortunately weren't the ones to discover it. It was discovered back in about mid-May, May 19th, by Japanese astronomer Koichi Itagaki. He was one credited for it. And the supernova itself is in what we call the pinwheel galaxy, imaged here. Quickly after the discovery of it, the supernova was determined to be a type 2 supernova, which we'll go into a little bit more about in just a little bit. But soon after the discovery of this, it was all over different newspaper articles and different websites like that. We actually discovered it through the Sky and Telescope article.
Yeah, literally just came up in my Google News feed, and I was like, oh, interesting.
Yeah, we're like, oh, that's pretty cool.
Yeah. So what's so super about them anyway? You know? So there are a lot of different flavors of supernovae, but type 2 are actually the most common type, and the subtypes that you get from type 2 are most often type 2P or type 2L. And spoiler, that we'll talk about later, our supernova is a type 2L. And type 2s are what a lot of people think of when they think of supernovae, if they have any prior knowledge about them. We call them core collapse supernovae because it is basically the result of a death of a really massive star that's 8 to 10 times bigger at minimum than our own sun. So a little bit about stars for anybody who isn't informed. So stars basically burn by fusing hydrogen into helium in their cores, and massive stars start out the same way. But because they're so big and bright and hot, they run through their hydrogen pretty quickly, and they start fusing heavier and heavier elements until they get to iron fusion, which, unlike the previous elements that it was fusing, actually doesn't output any energy. So the core doesn't have enough energy in it to support itself against the rest of the star, and the core ends up imploding, which ends up sending out a huge shockwave explosion, and you have, boom, a brilliant, bright supernova. This image on the right here is the Crab Nebula, which is a supernova remnant in our own galaxy, which is super pretty, super cool to look at. And it came from a type 2 supernova that was observed by ancient astronomers, particularly Chinese astronomers, in the year 1054, which is super cool.
So where is this supernova, like in reality? So pictured here, we have the Pinwheel Galaxy, or as we like to call it, M101, because there are so many different objects out there with the name wheel. We get them all confused. Like we have the pinwheel, we have the whirlpool, like they're all spinning. Cartwheel. There's
the Southern Pinwheel Galaxy also.
Yeah, we have too many to keep track of, but
M101 works.
We love M101. So in our galaxy here, if you're looking up in the night sky trying to find it yourself, if you're familiar with Ursa Major or the Big Dipper, you take the last 2 stars of the Big Dipper's handle and you kind of follow them upwards to make like a point, like a triangle going upwards, and roughly where they meet, that's about where in the sky our galaxy is. But M101 itself, it's 21 million light years away from us. And you can see in these big clumpy regions that we're pointing out on screen here, these are what we call H2 regions, which are big star forming regions. And the reason why they're so bright in this case is because they have lots of bright, young, hot blue stars.
Kind of stars that go supernova.
Exactly. And you'll see soon where, spoilers, are the supernova itself is near one of these regions. So I'm not going to tell you which one yet. So describing the galaxy itself, get into some galaxy morphology a little bit. This is classified as a type SAB RSCD galaxy.
Is that the alphabet?
That's part of it. So SAB describes the center bulge of the galaxy itself, the brightest part. SAB means S for spiral. AB for we're not sure if there's a bar in the middle of it. You can kind of see an elongated.
Yeah, it's kind of oblong.
Yeah, so we're not really sure. So we said it could be a bar. So that's what AB means.
Yeah, it's in the middle.
The RS part of it means that there's kind of distinct rings within the spiral structure.
Kind of. So
that's why it's in we put it in parentheses for we're not sure. And then the CD part at the very end describes the shape of the arms of the spiral galaxy, whether they're tightly wound together or they're kind of loose and fluffy. So starting at lowercase letter A, that would mean they're really, really tight. And then C and D goes towards the more like on the looser end. You can see that these are kind of all pulled out and kind of clumpy. And the reason for this is because M101 is in the center of its own galaxy group, which we call the M101 galaxy group.
We're really creative with these names.
Yeah, we keep it simple so we can remember it. But because of all these different galaxies in this group, these galaxies are actually pulling on M101 and distorting the tidal tails of this.
Yeah.
And including the supernova that we were observing, there have been 5 other supernovae and 1 nova reported since 1909.
So why us specifically? Why did we do this research? It was very much a case of right place, right time, right circumstances. So back in fall 2022, both Dylan and I took the Observational Astronomy class here at SUNY New Paltz, which is taught by our advisor, Dr. B. And this occurred right around the end of the spring 2023 semester. So we had all this knowledge already, And pretty much everybody was going home for summer break. But because both Dylan and I present in the planetarium, we were both getting emails from the planetarium director. And I knew he was around, and I saw this article about it that I was like, hey, I know this is bright enough that we could see it in our observatory. And so obviously we had to go out and try to find it. So I grabbed Dylan. I was like, hey, you want to come find a supernova?
I was like, absolutely.
Yeah, because who wants to do science alone? So, and of course, our advisor, Dr. B, was super duper excited that we were trying to go out and take some pictures of it. We hadn't planned to start research at this point yet, but when we were out there on our like first night, just trying to find it, probably one of the like best experiences of my life. On the right here, we have an image I sent to the Physics and Astronomy Discord here at New Paltz with the supernova circled and a direct quote, all caps, "We might have maybe found it," because it was really awesome. And just for a little perspective into what it's like to try to find a supernova, we have here on the left an image of the galaxy taken by some guys, Wallace and Provin, in 2006. That's kind of similar quality to our image, which is on the right, that we took the first night we went out to look for the supernova on May 23rd. And it was a little bit difficult. It was rough. At one point, both me and Dylan had our phones out. We had pictures up of the galaxy, of the supernova, of the galaxy without the supernova. And we were just trying to compare it, trying to figure out which one of these little dots is the supernova that we're searching for. And if you haven't been able to find it while I've been talking, there's a hint, there's a little bright region in this one right here.
One of the H2 regions I mentioned before.
Yeah, and it corresponds to this, and right above it in ours, this bright dot, this is SN 2023 IXF. And when Dylan and I finally found this, we, suffice to say, lost our minds a little bit, because it was literally like the joy of discovery. Even though we weren't the ones who initially discovered this, being able to see it for ourselves with our own images was an incredible feeling.
It was unreal.
Yeah. And so, of course, also our advisor was very excited that we had taken a bunch of images on it that first night. And she said, hey, do you want to keep doing this and do research on it and get credit for it? And we said, yeah.
Absolutely.
Absolutely. Say no more. We're on it. So what's the point of our research? There's a lot of, like there were some specific things we wanted to do, but there were also some more subtle things wrapped up in that. We had only like worked in the observatory for like less than a semester on like imaging things. So we wanted to be able to get better at imaging things to do more stuff like this. And then of course, like the standard ones, if we're studying the supernova, we're gonna monitor and record how the brightness or the magnitude of it changes over a period of time. And we also wanted to see how it changes in different wavelengths of light. And then using these magnitudes that we recorded, we wanted to create a light curve, which is just the graph of brightness over time, and kind of interpret it. And most importantly to us, because we both work in the planetarium and we do a lot of science communication, we wanted to be able to share our results, both with the scientific community, so that supernovae, which are not super well understood in some cases, could be studied more. And we also wanted to share it with just the general public, because there's a lot of astronomical events that happen that are very transient and not super common. So we wanted to be able to increase interest and awareness in these things.
Data collection. So how did we measure this? What did we do? So image here on the right, we have our lovely CCD camera. These are special cameras. They're not like your iPhone cameras, anything like that. These are scientific cameras that have powerful detectors that count the number of photoelectrons that enter the camera, or photons or particles of light. And these photons hit each pixel on the chip of the camera, and that is how we quantify the amount of light coming from the supernova so that we can turn it into our data. And what we did with this camera is, over the span of about 6 months, give or take, we went out every clear night that we were available, and we took images in 4 different color filters and sets of images in no filter. And each image had an exposure time of 82 seconds. And we took 5 to 10 images in each filter, including no filter.
Yeah, so it was, every time we went to the observatory, it was a while, 2 to 3 hours each night.
On a quick night.
Yeah, on a good quick night. Because I know some of you people here, the Mid-Hudson Astronomical Association, you really like your telescopes, you really like your equipment. Thought I'd give you the nitty-gritty details in here. So what we're working with at the Smolen Observatory, we have a Celestron Edge HD 14-inch telescope. So it's got a nice big opening. The mount we have that Dr. B says is pretty good is a Paramount ME mount. And then the exact camera that we're using is from the Santa Barbara Instruments Group. It's an STL6303E. This is a dual CCD camera, so we should theoretically be able to use a process called auto guiding, but we haven't been able to get it to work yet. We're working on it. And then to control the telescope, we use the SkyX Professional. And to take all of our images, first we had used CCD ops, which we had learned in observational astronomy, but then we transitioned to using the built-in imaging functions in the SkyX around September because we found it a little bit more user-friendly.
So before I mentioned that we took photos in different color filters, well, these photometric filters are listed here with our images labeled B, V, R, I, and none for no filter. B stands for blue light. V is our mainly visible light spectrum.
Corresponds kind of to green.
Yeah, kind of green if you're getting to the colors. R for red and I for the near infrared. And for our CCD, exclusive to ours, looking at this graph in the bottom right, this shows the peaks and wavelengths of the different color filters. First, starting from left to right, we have U for ultraviolet, which we don't have in our CCD.
We prefer using the none because honestly, like just having a slot where there's no filter in it, because you don't get a ton in there.
Yeah, with ultraviolet, there's not much there. So we have U, and then we have the B, and then shows where they each peak. We have V, R, and then I. And then, yeah, we have none filter because we don't have an ultraviolet filter, and just allows us to get all the light. We can't really do science with none filter, but it's good to have just to see like.
Yeah, because it's very specific to our CCD. So if anybody tried to go out and copy our data that we took in with no filter, they wouldn't get the same thing as us. So yeah. So a lot of questions I get when I show people images that we've taken is, are the images edited? The answer is yes, but not in like the Photoshop way. We do a process called data reduction, in which we have these raw images here you can see that are kind of grainy, kind of spotty. There's some weird bars in them. And we're just trying to study the supernova. We're not trying to study the defects in our camera. So we correct for the defects. So to do that, we take like 5-ish raw images. And then after that, we subtract something called a master dark, which basically shows you a lot of the hot pixels or bad columns in your CCD. We subtract that out of all of those images. And then here we have a master flat, and that's because a lot of the filters have little bits of dust on them, and they create these donuts, which we're not trying to take food pictures, we're trying to take space pictures. So the donuts gotta go. We divide this out. And then finally, we align all of the images in the stack because you take them at slightly different times, so they're usually in slightly different places. And we combine them and we get a beautiful image right here. This is an example of one in the R filter. So, you know, it's not the photoshopping they do on magazine covers, but we do edit them just to make them cleaner. So, yeah, we ran into a few issues.
Just a few.
While taking this data. It was a very long data collection period. There were some environmental factors because we started this late May. At that point, the sun was up until like 9 p.m. So we had to be out super duper late. And then, of course, there's our lovely upstate New York climate where it seems like it's cloudy 90% of the time. So can't take images on those nights. And then Dylan and I are the kind of people who mosquitoes are obsessed with. So
Yeah.
during the summer months, we were bathing in bug spray out there.
Having an observatory next to a small creek is not the greatest in those wet summer months.
Yeah.
But on top of all this weather and all that, you can see pictured on the right here, we have our lovely little folder of images that we call Thanks Elon, because we would have trails of satellites that would go through our images.
Sometimes they were planes, but we like having somebody to blame specifically. It was both annoying and kind of cool that I managed to get 2 intersecting trails in one picture at one point. And then, of course, there were some issues with the telescope. At one point, it straight up broke and we couldn't take data for a while. But we also, our mount isn't quite perfect. So if you look in this image down at the bottom left, our stars aren't really circular. They're kind of streaky.
Yeah, kind of smeared.
We call these beans. And whenever we were taking data together and I would see an image pop up that was all streaky, I would just yell beans and Dylan would be like,
Yeah, just like, all right, scrap it. We'll just do it over.
Yeah. Though you'll notice some of our images still end up, the stars are not perfect circles, but they're gets to a certain point where it's like, okay, it's good enough.
Yeah, it's circular enough.
And then lastly, just we're people. And sometimes it was very hard. Oh, suddenly all of the clouds cleared up and it's a clear night. Wow, I had like really important plans tonight. I can't go to the observatory.
Or I just worked 8 hours and oh, it's going to be clear tonight. I guess I have to spend 3 more hours looking
Yeah.
at this galaxy.
So it was a little rough, but we persevered. We overcame. Thank you. So this is a time-lapse GIF of all of the images we took with no filter. And if you watch the supernova specifically, you'll watch over time as it gets dimmer and dimmer. This is kind of an example of it qualitatively, like just measuring and seeing, oh, hey, this bright thing started getting a lot dimmer. I apologize that the galaxy looks slightly different in each image. We were struggling a little with this and the brightness contrast levels did not go to the same thing for each image. This is our last image and then it pops back up to the beginning. I'll let us watch this for just a little while, just to kind of absorb.
Yeah, you can really see how when it reaches its dimmest that we observed and how it just jumps back to how bright it was in the very beginning. It gives like a sense of, wow, we looked at this for quite a long time.
And this is also a really great example of how our skills improved over time of taking images because the focus gets a lot better. We get things in frame slightly better. And we generally see less of the like defects. There was actually technically one night we took of data that I did not put in this because the images were frankly embarrassing. So
yeah, something happened that night, but we're not sure of.
I was out really late. I don't even know what happened. But we'll let this hit one more time and then we'll switch slides. Favorite part is around like the middle of August. We get some really good images like September and October. Yeah, all right. Now, data analysis. So we've got all these pretty pictures. How do we get the data out of them? So these are all like special file types that have the data encoded into them. That you use special software or like other like coding things to get it out of. We use the free software Astro ImageJ that we were taught how to use in observational astronomy. We used a tool called aperture photometry, which basically it takes all the pixels that we tell it to take, for example, all the pixels in the supernova, and it counts up how many photons are in each of those pixels. And then because the sky behind it has its own like level, it's not just completely black, it would also take the level of the sky behind it and it would subtract that out to get us to our to a value called the source minus sky. So basically we would run this tool where it selects these little targets on things we wanted to measure, and then it spits out a bunch of data, but most important is source minus sky, because we can do math with it. And I'm so sorry for people who don't like math very much. We actually never did this ourselves. We put it in Excel. But to get the magnitude from our source minus sky value, we could use this equation down here where the m is the magnitude. And then this c right here is a constant that depends a lot on seeing, and your equipment actually changes from night to night. And if you know anything about math, you know when you have one equation and you have two things that you don't know the value of, you're kind of in trouble. It's hard to solve. So let's see how we solve it.
So in order to get the C value of every filter of every night, what we did is we had to find stars that we actually know the magnitude of as one of our unknowns. So we took a look at our images that we took, and we tried to find bright stars that we knew the magnitudes of. And to find the magnitudes, we used a few different databases using the website Aladdin, and it gave us the magnitudes in the B, V, and R filters, and that gave us the C value. So you'd take the magnitude from the database, you plug it into the equation, and it spits out the C value for that filter on that night.
And then using that C value, we can get the supernova's magnitude for that night, which is great. But there is one filter missing from this, and it is my favorite problem child, the I filter. So not a lot of people measure brighter things that we can see in the I filter. So we had to get a little creative, had to ask for some advice from our advisor. We ended up doing something in which there was this guy, Landolt, who published this whole huge paper of standard star fields in which he had measured stars in the U, B, V, and R and I filters. And so basically what we did is we found one of his star fields. This is just a portion of SA94, has this really cute little galaxy in it, which is, for anybody interested, UGC 02403. Very catchy name. But so this is his image. And then on November 20th, I went out 2 a.m. and I took this image of that same star field in the I filter. And then immediately after that, I went back to M101 and I took a picture of M101 and the supernova. And with having these magnitudes, I'm just gonna go back a slide, I could then use the C value that I got from those to measure both the supernova on November 20th, and then also these standard stars that we had been using for all the other filters. And so with these magnitudes known in the I filter, we could apply that to all of the other days worth of I filter data that we had. So it was difficult, but you know.
Results in discussion.
Y'all ready to see some light curves? Yeah, so the first one we have is the B filter. So just to kind of explain our graph here a little bit, on the x-axis, we have the observation date. So our first observation was May 23rd, so this does start a little bit delayed. And then on the y-axis, we have the apparent magnitude of it. One thing about magnitude is that it's a scale that runs backwards. So the smaller the number, the brighter something is. That's why these numbers get bigger as they go down. And you can kind of notice here, so Supernova 2023 IXF that I alluded to a little bit earlier, it is a type 2L supernova, and the L stands for linear, which means after its brightness peak, it decays, like the brightness decreases in a relatively linear fashion, which you can see pretty well right here, until it reaches a certain point where it drops off, that we like to call the swoop, because it looks like a little swoop, and then it kind of starts decaying a little bit slower. So one thing in particular for the B filter graph, you can see we have some uncertainty bars on these. It gets a little bit weird towards the end of our observations, because we basically our limiting magnitude for what we were doing was about 16. So down here at the end, our uncertainty should be a little bit greater because the Astro ImageJ that we were using to analyze the images was actually struggling to even recognize the supernova as not just background noise. So these need to be worked on a little bit. But it's really cool to see the beginning here. We didn't quite catch the peak of it because it peaked before we started observing it, because it peaks very fast in B, but it's still really cool to look at. And next up we have the V filter.
And as you can see with the V filter, it still has that linear shape coming down towards the top of it. Also has our favorite little swoop after that. And as you go later on through the data, you can see that our error bars or uncertainty bars are a bit larger, and we're more confident in these because it's not quite reaching the limiting magnitude of 16. It's the whole graph is kind of shifted up a little bit because with each filter of light, the supernova peaked in brightness at different times, but we'll
get into that.
We'll come back to that.
We'll come back to that. So we feel good about these uncertainties here. We also did miss the peak in V as well, unfortunately. Next up, we have the R filter for redder light. And the most exciting part is that we did manage to catch the peak of the supernova in the R filter. Yeah, thank you, thank you. It happened around like the last couple days of May, first day of June. So we have a peak here, and you can see we don't have as many data points like in this area because Canada was on fire, and then there was rain, and then the telescope broke. But we have, this is somewhat linear-ish. And then we have the typical swoop here. And we feel good about these uncertainties for the R filter. And lastly, my problem child, the I filter. So the I filter, we also caught the peak of around the same time as the R filter. And this actually is like a really good shape for a typical type 2L supernova. There are uncertainty bars on this graph, but they are so small that you cannot see them, which we don't feel great about, but we're working on a little bit to try to figure out how we can make these uncertainties more certain, you could say, even, so that we have a little bit more confidence in them. But other than that, the I filter did actually turn out really, really well in terms of this light curve. And here we just have them all combined together on one graph, so you can see the differences in each filter. So initially, the supernova was the brightest in the B filter, but quickly, very, very quickly, it becomes the dimmest. And then you do see these peaks of I and R, and you kind of see how later on, they kind of settle into a pattern in which the magnitudes are like a set distance from each other from each filter. And I could not tell you why that is. So just preempting that question. But there are a couple features of this graph we want to get into. But before that, how good are our results? Honestly, completely open here. This is our first research project. If we got totally terrible results, that's science. We're learning. But we actually took all of our light curves and we met up with our advisor, Dr. B, and she pulled up the light curve from the American Association of Variable Star Observers, which is like a coalition of both amateur, professional astronomers and like observatories who take data on objects like this that are variable, and they make light curves out of them. And when we were looking at it, we were like, oh, these are actually really, really similar. You can see like this runs the same dates that our like observations were, and you can see the big clump around 11 magnitude, and our big clump is around 11 in magnitude. So this was pretty good. And honestly, sitting in the office with Dr. B comparing these two, we were kind of gobsmacked because we're like, wow.
Yeah, we did that.
Like first try, we were able to get really good data. So that was super exciting and super validating, honestly. And then.
So looking at the graph itself, we were talking a lot about this swoop that we have circled here in red. This swoop is the transition from seeing the light of the supernova to seeing light powered by radioactive decay. So that swoop is that transition point. And the reason we see that is because supernovae form most of the universe's heavy elements that aren't the basic hydrogen, helium, everything there, the heavy ones past iron and all of that are typically radioactive, those are formed in supernovae. So we're seeing the creation of that in our light curve, which is actually pretty cool.
Yeah. And one other thing that I frequently get questions about when I show people this is, so why does the supernova peak at different times in different wavelengths? And boy, is that a hard question to answer, but I'll do my best. So it kind of boils down to temperature and the supernova's ejecta, which basically when it first happens, when the core collapses, there's still the rest of the star around it. So there's a bunch of material like gas and such that's around this, and it's kind of blocking the shock wave that's trying to get out of it. We call this material the ejecta. And so because this shock wave is very, very powerful, but the ejecta is really, really dense, it's kind of like they're locked in a battle, trying to overcome each other. The shock wave ends up superheating and pushing the ejecta out. But because the ejecta is trying to like cool down because it's getting so hot, it releases photons, but those photons still can't quite escape the ejecta. So there's like this big buildup of light and heat and energy. And finally, the ejecta gets thin enough that we can see some extreme heat escaping it. And basically, things that we see in bluer wavelengths tend to be hotter and redder wavelengths are cooler. If you look at a candle flame, the hottest part is the blue part, right? So basically, when we see all of this extreme heat escape the ejecta, we see the bluer, hotter wavelengths peak quickly. And then as it cools down, we start to see peaks in the redder wavelengths like R and I. This could be a bit of an oversimplification and it could be wrong. So if you hear anything else, let me know because I'd like to know too. So that's my best explanation for that.
Conclusions and future work. So what did we gain from this? Well, first of all, this was our first time actually doing research in our field, which is pretty awesome. And because of that, this is really invaluable experience for us in the field because it would help us to want to keep doing stuff like this. And it's just a great experience to be able to do here on campus, given we have the equipment for it.
Yeah. And because as I've said, both Dylan and I are science communicators working in the planetarium, it was really important for us that we got a chance to talk about this a lot. We got a chance to talk about it here. Back in September of last year, there was a summer research symposium here on campus we were invited to, even though we didn't have everything and we were only halfway through data collection, they still let us come and talk. And then back in January, I was able to go to the conference for undergraduate women and gender minorities in physics. And I was able to present a poster there, which you can see at the bottom, which was a really, really awesome experience and also helped inform me on the kind of questions that people would ask and how I might be able to answer them.
And on top of just everything, from being out at the observatory for months on end, getting all this expertise.
We basically slept there.
Yeah, basically, we'd have set up our sleeping bags where we pay rent. But since we've been there so much, we were like, we have all this knowledge. We were actually able to become teaching assistants for the observational astronomy class that we learned how to do all this in. So as teaching assistants, hopefully we're going to help that current class maybe get into something like we did and lead them from there.
Yeah. And so what are we going to be doing in the future? So a few of my friends already know this because I've already told them, but something really exciting is that we're actually going to be trying to publish this research. There is the Journal of Undergraduate Reports in Physics, published by the American Institute of Physics and the national branch of the Society of Physics Students. So after a little bit of polishing, we are going to be submitting to them and hopefully we'll be real published researchers soon, which is exciting. Thank you.
Thank you. And on top of getting our research formally published like that, we actually plan on, after we critique some of the uncertainty bars and everything like that, we're going to submit our light curves to the AAVSO light curves that we were comparing our data to. So our data can be a part of everyone else who's looking at the supernova's data. So if anyone else wants to start doing research and work with the supernova, our work will be a part of that.
Which is super cool.
Yeah, super exciting. So what did we just talk about for like an hour? So we weren't the ones to discover it, but we looked at supernova SN 2023 IXF that started back in May of last year, went through 6 months of research of that. We talked about what supernovae themselves are and why we decided to study this one in particular. We took over 100 plus images of this galaxy and this supernova, which is a lot of storage space on my hard drive.
Oh my God, yeah.
We took images that you saw were both pretty looking, and we could do a lot of science with them. We talked about what we did with these pretty images and how we analyzed them, got all the data out of it. We showed you our results, our light curves that we get from all of our images. We described what was going on in the light curves, like with the jumbles in the beginning, the peaks, and what the swoop meant. And we compared it to the AAVSO to confirm that we actually knew what we were doing and that we actually got pretty cool data. And we told you that we are publishing our research in this coming month.
Yeah.
So very exciting.
Yeah, super great. And of course, just wanted to mention a few people here at the end who are instrumental to this. Of course, Dr. Amy Bartholomew. Her inbox is probably just filled with my name because I ask her so many questions, but she loves me, it's fine. Dr. Eric Myers, of course, who set us up here at MHAA. He's given us some great advice about our uncertainties, and he helped fix the telescope when it was broken. Raj Pandya, who is the planetarium director, one of the first people to encourage us to share our research when we were doing some planetarium shows, also helped with the telescope issue we had. Dr. Catherine Hearn, who ran the summer research symposium that we presented at, as well as who helped me make my poster for the QIP conference I was at. I want to thank my sister, Sylvia. She helped us make that GIF that you saw of the time lapse because we couldn't make it in the normal software we use, and that meant we struggled.
Yeah, we didn't have the technology.
Yeah, and then of course we wanted to thank the MHAA for letting us talk here about all of this. And lastly, of course, they know who they are, our friends and classmates who provided us with both advice and moral support just throughout this whole long process. So with that, we'll take any questions you guys might have.
Questions and you can answer with the other one.
Yeah.
Okay, so
I'll hold
that.
mine.
Okay, my question is about the swoop. If we are starting to see light from a different source, why does it get dimmer? You know, in other words, the initial flash dims, but you know, that seems to be quite a drop off. And if we're getting a light source, a different light source, why doesn't it level off or even go up if we're contributing nuclear, decay, right?
Yeah, so that's a great question. So basically, the radioactive decay was always there in the light curve. It's just that the initial light from the explosion was always overpowering it until a certain point. And because that light was so intense, when it finally cools enough that we kind of stop seeing it so much, it really just shifts over to the decay, which is a lot slower of a process. And so it's kind of a bit of a dramatic drop because the decay is a lot slower and it doesn't contribute like as much light.
So I guess, yeah, the initial flash drops off. I mean, it seemed to go on for a couple of months and then drop off pretty quickly.
Yeah, so that I think is relatively typical of a type 2L supernova as far as I know. Though there's still a lot of questions about these kinds of things. But you know, essentially like there's only like so much like light and heat that's really intense enough to just completely overpower like everything else that's happening.
Thank you.
Mhm.
After a star of this size goes supernova, what's left over?
So when a star like this goes supernova, as we image towards the beginning, like we showed the Crab Nebula, that's kind of what's going to be left after that. But we're not really going to see what looks like the Crab Nebula because this supernova went off in another galaxy. So eventually this is just going to fade to kind of nothing, but there will be a supernova remnant left over afterwards.
But there's no core left, no white dwarf or neutron star or anything.
There will be a core left over, depending on how massive the progenitor star, or however you say it, the star that it was before it exploded. Depending on how massive that one was, you'll get different remnants, but all of those remnants are usually very, very dim. So it could be a white dwarf, it could be a black hole. But it's one of those things that would be really, really hard for us to see. And in most cases, especially like in our own galaxy, usually it's actually often easier to see the remnant than it is to see like the actual supernova remnant. So like the expanding cloud of material than it is to see whatever was left behind of the core. Yeah, Crab pulsar, really rough to see, but the Crab Nebula is beautiful. So yeah, and that's in our own galaxy. So I mean, you know, maybe when we get some absolutely insane space telescopes, we might be able to see something, but for now, yeah.
Hello. That was awesome.
Yeah.
Thank you.
I have two questions that inspired me to ask this question, which is, do you know the mass of the original star, and is there a way from the light curve of the resulting explosion to understand how big that star was?
We do not know the mass of the original star. And as far as I've read of other people's research, they don't either. The only thing, so the light curve tells us what type it is, and the type does often also have implications about like the composition of the star. For example, the difference between a type 2L supernova and the other common type of type 2 supernova, which is a type 2P, is that stars that go supernova in a type 2P explosion have a thicker envelope of hydrogen around them than type 2Ls. So we can tell a little bit about the composition, and if we had a spectrometer that we could use in the observatory, we would get even more information. I haven't looked into a lot of data from people who did measure this supernova with spectrometers that would give us some more information, but I'm not sure we could exactly tell you like it was a M1 star.
Yeah, or like it was.
Why would I say M? Like an O4 star. I don't know. Yeah, so unfortunately, no, we can't tell a lot, but we can tell some things from the light curve.
Cool. And then when you calculate C for the infrared, the problem child, I'm fuzzy on how we learned how to do this, but does it impact the accuracy of C if that star fields from that paper is somewhere far away from your galaxy and your image? Like, or
so mostly I think I may have not mentioned this. So obviously M101 is an Ursa Major. The star field that I was imaging was in the constellation of Cetus. pretty close to Pisces. So it is rather far away, but because C is based a lot on seeing conditions,
Right.
because right after I took the images of the star field, I went directly over to M101. We think that is pretty much enough to kind of compensate for that.
Okay.
And because we had all of the same exposure times and such.
Cool.
Yeah.
Cool. Thank you.
So in the picture that you had before the star went supernova, can you hear me? I got this?
Yep.
Okay.
It's done to be close to you.
Oh, okay. Could you see the progenitor? Thank you for feeding me that word because I forgot what it was.
Probably not.
Because I kind of, when I saw your two pictures, I
Yeah.
thought I saw something there.
So there was definitely, I wonder how no, so
But in their images, I'm talking about.
let me flip back really quick. When we get, I wonder
gotta-
if we used any of our later, when we get our later images. The question. Okay, so basically when we get, one thing we noticed in our later images is that there is a slight background behind the supernova. So there's an H2 region right beneath it, which is very bright, and there's likely like a lot of, you can almost kind of see it in some of these. I wish I could pause this, but I do not know how. But there's like a little bit behind it. So honestly, if we could see it, it was probably mixed in with a lot of other different things.
Okay.
Yeah, it would be really difficult to try to resolve a single star.
Yeah, in a galaxy so far
Okay.
away.
Yeah.
And did you have coordinates to work with from
Yes, so we did have some coordinates, but honestly, we usually just worked with the coordinates of M101 because I mean, with our with the field of view that we have with the CCD, if we got the center of the galaxy in the photo, we would get the supernova in the photo. If that makes sense.
I think so.
Okay.
Howdy. Fantastic job. That was so
Thank you.
cool.
Thank you.
My question is, since you guys have spent such a significant period of time dedicated to this research, do you think maybe it was a whole lot of work and maybe you wouldn't be interested in it again in the future, or did you enjoy it so much that you hope to do it again in the future? And if so, what would you be inspired to look at next on top of something incredible as a supernova?
Good question.
Great question. First of all, both Dylan and I have said to each other, if there's another supernova that goes off tomorrow, we are studying.
We are out there.
But we may, because we're helping out in observational astronomy, we would probably pull in some of the observational astronomy students into it. Was that pandering to us? Were you trying to? Okay.
No.
But no, we would absolutely be willing to repeat this kind of thing. Though I do think it would be very worthwhile for us to bring other people into it.
We don't want to have all the fun on our own.
Yeah, we got to give some other people some chances.
Yay.
Yeah.
But in terms of like continuing going about looking at doing cool research like this, currently this semester, I'm actually out of the observatory and I'm looking at different variable stars and various star clusters. I'm looking at the globular cluster M3 and a few open clusters, and I'm going to make a kind of something like this little movie GIF here of showing how the variable stars dim and bright over time. So it could be like a little fun little, just like showing the variable stars like that.
Cool.
Yeah.
Thank you.
Steve.
So there was a new supernova in January, so just curious if you're going to cover that.
Was that in Andromeda.
It was in NGC 4216, a spiral galaxy.
That one, I don't know that I've heard of that one, but do you know the magnitude of either the galaxy or the?
Not offhand. I could send you the article. I just remembered seeing it a couple days ago, and so you mentioned that. I
Yeah,
thought I'd look it
honestly,
up.
the thing is, the reason
It's not as big as M101.
yeah,
for sure.
so the reason that SN 2023 IXF happened to get so much media coverage is because it was called like the closest supernova in the past 5 years, and it was bright enough that a lot of people could actually view it.
Yep.
So my gut instinct is that because that information didn't go around a lot, it probably is something that might be either on the borderline or straight up just too dim for us to currently observe.
Okay.
So just with what we have right now. But I would if I could.
Yeah,
I'll send you the
so-
article. You can take a look.
Yeah,
Yeah, that'd
If
be
it fits
great.
your
Yeah.
profile.
absolutely.
You have another question? That's fine. I've got one too, and then I've got a comment.
Okay, so
Go ahead.
Dylan, you're graduating,
Yes, this semester.
and Stoker, you
Also graduating.
oh, so now what are you gonna do?
So I'm actually currently trying to find jobs at either planetariums or observatories, doing like either planetarium shows or science communication, also like at science museums, just because I really love communicating difficult astronomy topics to people in ways that they can understand.
Cool.
And I'm kind of torn about which way I want to go. I absolutely love looking at galaxies because like looking at like the structure of spiral galaxies, they're just so like pretty to look at, and I love working with them. But at the same time, I'm a geology minor, so I love like what's below us and how I can apply like the terms of geology here to different planets and moons in our solar system. Like if I were to look at Mars and be like, oh yeah, if I look at rocks here, see them in a layer, oh yeah, the oldest stuff is at the bottom, younger stuff on top. You can apply that out on Mars and be like, oh yeah, that at the bottom there, that's the oldest, and we can date it like that one day in the future when we send people in research there for that. So I really either want to get into planetary science like that and study all of that and go to school for my master's either out in Arizona, or I'm thinking Washington State because they have planetary science master's programs like that. Or I could go the route of getting into, I don't even know how you would classify it, looking at galaxies. I love the observational aspect of
I know
it.
Phoebe knows about that stuff.
Are you familiar with the dark galaxies that were just recently discovered?
Yeah, I read a little bit about those, but
That's mind-boggling.
yeah, it's a lot to wrap my head around too.
Me too. Thank you.
So I have one question about the filters. Can we go to the curve for your filters?
Oh, the combined curve for all of them?
Yeah, just to show where the filters are.
Oh, the graph that shows.
Right, the graph
That's
there. So I know these are the standard filters,
Yeah.
but it looks like they each peak in their own place,
Mm-hmm.
but it looks like there's some gaps. Are there?
I mean, yeah. So this means that they like peak here, but they are still like obviously.
They're still
taking-
getting some light
Yeah.
there, but are there filters that people might use that would get like 525 or looks
Um,
like 500 exactly, or 740?
Yeah, so there are different kinds of filters. So these are the Johnson Cousins filters. They're what we call wide passband filters
Okay.
because they go over a larger range of wavelengths, but there are specific filters that correspond to very narrow like ranges or narrow bands. I think there's like some specific filters for like O3.
There's definitely a hydrogen filter.
Yeah, definitely a hydrogen filter. Yeah. So we were just
Yeah.
using wide passband filters here to get kind of just like a general sense. But yeah, there are absolutely filters that do very narrow wavelengths.
I don't think you get filter sets that also have a very flat top and pretty sharp drop. And they have less of a gap in between next one covers.
Yeah,
Yeah.
yeah.
So I also want to make a comment. I don't know if I can pull this off, but while I think it's really interesting, let me see if we can get this on the screen with our camera inside. In the room, we've been putting the slides up on the left and then the crowd who's joining us remotely on the right. And one of the people out there is Michael Goldstein, who's actually imaging right now. So we can't really see him. Michael, you had your light on earlier. I don't know if you could turn it on.
I'm sorry, can you hear me?
Yes,
I had no idea you were gonna do this.
I didn't. I know. I
What
didn't
do you
want
want
to.
me
I
to
don't.
do? Share my screen?
I know. I just want to show that you're joining us here while you're imaging, and I don't know if you can turn your red light on or not, so we can see it on the screen. But
Oh,
is that can interrupt anything?
well, no, I can share the screen if you want to see what I'm
No,
looking
no,
at.
no. I want to see you.
Oh, you want to see me? I'm sorry. I can turn the
Turn
light
your
on.
headlamp on. The way you had it on earlier.
Well, I got, can you see me now?
Yeah. Okay, so he's as we've been going through the talk, he's been on the side of the screen working on his imaging. So I think I find that amusing. So that lets me segue into the fact that Michael will be our speaker next month. He's going to tell us about what is it? Electronically assisted astronomy, right?
Yes,
And-
that's what I'm doing right this second. I am
Right this
imaging
second
ARP
during-
145.
Okay. So so we look forward to that as well.
Right, wonderful.
Yeah, if you like galaxies, check out the ARC catalog.
That is a good catalog. I love all of those.
That's ARP or AARP? That would be my catalog. Okay, any further questions? And this was marvelous. Thank you. Thank you guys. Can't do that. Bang everybody's here. All right, beautiful. Just before we go, thanks very much. It was really cool. Before we go, we didn't get to mention it, but anybody who would like to join us, we usually go to Pasquale's Pizza right up the road. Have a little nosh and carry on with this a little bit if you'd like. So real rough guess, so we know how big of a table to get. Anybody interested in joining us tonight? 1, 2, 3, 4, 5, 6, 7. Get a big table. Looks like 10 or 11, maybe 12. Cool. Thank you very much. We'll close the meeting and we'll see you all next month.